All right, welcome everybody. This is Astronomy Modeling with Rubin Observatory. This is our Exploding Stars edition. My name is Dan Peluso. I'm a teacher and researcher with Griffin Academy and the SETI Institute, and joined by Artist and Justine. I'll let them introduce themselves in just a moment, and we'll get started. I've been involved with astronomy modeling for several years and did my PhD in astrophysics and also incorporating astronomy modeling. There's an astronomy modeling with exoplanets workshop, which we'll talk a little bit later today, which has inspired some of the work that's done at AMTA in modeling, and Rubin Observatory, which you'll hear all about from artists and Justine in just a moment, has some very exciting things that we're going to be sharing with you. And this is a part of a series that we've been doing. What was the first one that we did? Was it back in the fall in October or
Yeah,
November? I can't
I
remember.
think it was October, and we did
October.
surveying the solar system.
Hmm. Yeah, so welcome back everyone who has been to those others, and if we have anybody new, welcome to your first one with us. And Artist and Justine, would you like to introduce yourselves, and then we can dive right in?
Hi, everyone. I'm Artis Harold. I'm the education specialist for Rubin Observatory, formerly a classroom teacher, primarily high school level. And Justine?
Hi, everyone. I'm Justine Shane. I'm an education specialist for NSF Noir Lab, and part of my role involves supporting Rubin Observatory. So thank you for joining us here today as we introduce exploding stars to you and highlight all the modeling components with this investigation. We also invite you to tell us about yourselves. So if you could type your name, where you're from in the chat, what is your current role if you're a teacher, and what grade levels you work with. And then I'll turn it over to artists.
Okay. Um, so we're just going to start with putting our code of conduct up. We will be working today later on in breakout rooms. And so some of you may have been at some of these modeling webinars before for Rubin Observatory. Maybe this is your first one. So we want to invite all of you, regardless of your level of background or expertise, to feel like you have an equal seat at the table today, and ask that you try to give us your undivided attention as much as possible, so that we can make this a great experience for you. Thank you. So what we're going to do today is we'll talk a bit about the Exploding Stars investigation, as well as Rubin Observatory, and the different resources associated with this particular investigation. But these webinars in particular have a special focus on, if you are working, teaching in a modeling kind of framework, a special focus for you about how you might effectively integrate this into a modeling curriculum. And also, some of you are teaching with the American Modeling Teacher Association astronomy units. So we're going to try to show you how to plug in and integrate this investigation into your current storylines. For those of you who might not be familiar with Rubin Observatory, our observatory is located in Chile. You can see its location there on the map. We are a U.S. publicly funded observatory. About half of our funding comes from the National Science Foundation, and about the other half is from the U.S. Department of Energy. Our observatory is right now just finishing its construction phase. We hope to see our first look images sometime this summer. Our observatory is named after Dr. Vera C. Rubin. Vera Rubin was an astronomer who was very involved in the study of dark matter. And although she did not invent this concept of dark matter, she was the one to provide convincing evidence over decades of research that there, in fact, is evidence for dark matter around galaxies. She also was a very strong advocate for women and early career scientists in astronomy, because she believed that anybody who wanted to do science should be able to do that. And we'd like to think that we take that attitude into our investigations too. So design them for anybody who wants to be able to do science. Just a bit about our observatory, if you are not familiar with it. We're going to introduce three unique aspects blended together. One is using the largest camera ever built for astronomy with these very wide field of views, very sensitive camera. We'll be taking these very large images of the sky. We intend to image the entire sky possible from the southern hemisphere every 3 to 4 nights, and we will repeat this imaging routine over 10 years of time. Because we have this very sensitive camera, we also are able to see faint objects, not only on the first pass through, but over time we'll be co-adding these images in 10 years. And this capability will give us a way for us to build a very dynamic view of the universe, because we'll be able to see those changes over those 10 years. So as I just mentioned, we're going to be taking a lot of images over 10 years, and that will give us an ability to look at all the changes that happen in the night sky that are visible from our location, and not only in very high definition, but also the large scale sky too, as well. We can go on. Rubin is focused on 4 key science areas. One is the study of dark matter and dark energy, which is one of the reasons that we've named our observatory after Vera Rubin. We also are going to be looking at the structure and formation of the Milky Way, because we're going to be cataloging and looking at the compositions of billions of stars, literally. We're doing a solar system census, which we hope will over that 10 years, quadruple the number of known objects in our solar system. And finally, we're going to look at all sorts of ways that the sky changes, from moving solar system objects to supernovae to other kinds of optical transients and variable stars. So those are our 4 main science areas. And our investigation today, exploding stars, you see fits into this last category of the changing sky. Every night, we will detect about 10 million changes in the sky. And out of all of those changes that we detect every night, we hope to detect about 1 million new supernovae per year. So you can see that we're going to be detecting lots of supernovae. Right now, the current number of known supernovae is under 20,000. So you can see in just a very short amount of time, we're going to surpass that number. And getting all this data on supernova is going to be very important for helping astronomers construct better ideas of the distances to galaxies and positions of that in the universe. That in turn sheds light on the distribution of dark matter, dark energy. So we're going to just look a little animation here, and that is, how are we detecting supernovae? Well, the way that we detect anything that's changing in the sky is by a process called difference imaging. And so what we'll be doing is taking images of the sky and comparing them against a known template. And by subtracting off the template of stars that we know should be there unchanging, we'll be able to see the things that remain. So we call this difference imaging.
The universe is a
And
dynamic
Justine,
place,
is the
but
video
how do
not-
scientists spot changes in the cosmos?
Okay.
First, they need to know what stays the same. Every night, Rubin Observatory will capture new images of the sky. Over time, scientists combine the many images of an area of sky, producing a template image of how that area typically looks. When new images are taken, the template image is subtracted, pixel by pixel, leaving only the changes, a technique called difference imaging. Whether they're flashy like supernovae, on the move like asteroids, or pulsating like variable stars, Rubin will find about 10 million things that change every night in an epic feat of spot.
In an epic feat of spot the difference. Okay. Now a little bit about our investigations. We have right now currently available 7 free investigations that you can use. They all incorporate authentic data. They all integrate into subjects commonly taught in an introductory astronomy course unit, and also many of the same kinds of things that you teach in physics. There's a nice overlap between the concepts of these investigations and the physics concepts that you may be teaching. So you can see exploding stars as one of these 7 that we're going to share with you tonight. All of these investigations are appropriate for introductory astronomy students. We don't put a specific grade level on them because we know you as the expert professionals will modify as needed to suit the particular needs of your class. But we found that they work well all the way from advanced middle school students through the introductory astronomy 101 type student, non-science majors at the college level. Because all you need to do is go to a website to use our investigations, you can use them for online classes as well as face-to-face. Now, all of these investigations use authentic data, and if you've ever dealt with authentic data before, you know that it can present technical and time challenges for you as an educator, because we only have so much time to spend on any one topic. So we've considered these needs. We've built for what you need to be able to do in a certain time frame. So because of that, you have nothing to buy, nothing to prepare ahead of time. You don't have to install special software, learn software query routines, teach your students how to use software, and we can have these ready to go. So like tomorrow, if you wanted to do these with your students, you should be able to work on them. Right now, 4 of our investigations are in Spanish. We're working toward building all of them in Spanish as well as English. And again, as I mentioned, totally free. We've designed them to all be done in about 2 hours or less, depending on what kind of support materials and add-ons you integrate with the investigation. Now, this is a really, really important slide. And so what I'd like to ask you all to do right now is open up a tab on your computer where you can put this particular link in. Justine has just put it in chat as well, where it says ls.st/xstars. This is what we call our workshop links document. It will give you a quick way to get to any kind of materials that we might be talking to you about tonight, as well as some things we don't have time to talk to you about. So at the very top, where you see in white, where it says Exploding Stars Investigation link, in a few minutes, when you click on that, it will take you directly to our investigation login. But notice there are a lot of other materials, such as the teacher guides and standards, links to our phenomenon, which Justine's going to talk to you about, links to an introductory video that we'll show in a few moments, all the different sorts of assessments we have, and other materials as well. So if you have this linked, then anytime after the workshop, you can go and check out these links directly. Not only does it save time right now in our workshop, but if you want to use any of our assessments, you need to create an account to view them because we don't want students to get in. And so this will help you jump over that account link right now so you can see views of the assessments that you might want to use.
Where are we in the universe? And how do we know? If we could make a detailed map of the universe, showing many different galaxies at different times, we could understand more about its structure and how it's expanding over time. Supernovae help us do that. Not only are they the cosmic explosions of dying stars, they're also great tools for measuring distances in space. Certain types of supernovae, called Type 1a supernovae, explode in a predictable way that allows scientists to compare them and figure out their relative distances from Earth. When you compare them, a Type 1a supernova close to Earth will look brighter than one far away, just like a flashlight in your face looks brighter than the same flashlight across the street. Type 1a supernovae are some of the brightest explosions in space, and that's how we can see them from billions of light years away. Their glow started traveling towards us billions of years ago, which means we can also use them to learn how the universe looked back then. With more observations of Type 1a supernovae in all directions, we can refine our map of the universe in both space and time. Scientists have been working on this project for a while, and they've found some surprises. When scientists in the 1990s looked at their space-time map, they noticed that the universe's expansion hasn't been slowing down over time like they expected. Instead, it's been speeding up. We don't know exactly what's causing that, but our best explanation is the existence of dark energy, a mysterious force pushing galaxies apart in the universe. Type 1a supernovae are great tools to help us learn more about dark energy, but they're rare to see in any one galaxy. For example, you'd have to wait about 500 years to see one in the Milky Way. We need more supernovae observations if we want to improve our cosmic map, and that's where Rubin Observatory comes in. Rubin will scan the entire southern hemisphere sky every few nights for 10 years, observing billions of galaxies and finding lots of Type 1a supernovae. Every few months, Rubin will detect more Type 1a supernovae than have been observed in all of history. That's a game changer for refining our map of the universe, learning more about dark energy, and maybe even revealing new cosmic mysteries.
Each one of our investigations is designed to support the next generation science standards. And so you can see that we identify each investigation with a kind of tricolor statement that picks out which of the science and engineering practices, the DCIs, the core concepts that we're highlighting and working toward in this particular investigation. So you can see here, we're talking about types of stars, fitting models of light curves, which we'll be going into in more detail, learning about supernovae, measuring their magnitudes and their distances to galaxies. So hitting that idea of measuring distances in space. Every one of our investigations is designed as a drop-in lesson that you can use wherever you see fit in terms of what you're teaching in your units. And so because of that, we don't intend to try to teach everything you might need to know about that particular topic. So we've identified two things here that we think would be helpful that your students are familiar with before you get started on the investigation. The concept of standard candles and the magnitude scales. Now, having said that, if you haven't taught that, we feel like they can still successfully navigate the investigation, but you might have a few more questions, a few more hands going up that you might have to attend to as they work through learning the introductory material in the investigation. Because our observatory is not yet producing its own data, we are using authentic data from other surveys and observatories. This particular investigation uses supernova data from, excuse me, the ZTF project, and using the alert stream brokers Antares and Lysair to kind of identify and filter out appropriate supernova for this investigation. Once we have our own data, we'll sub out what's there now with our own data. Now, each one of our investigations come with a lot of other things besides the online component. We have a pre-test, post-test that's a little short multiple choice type test you can apply before and afterwards to measure learning gains. We have a phenomenon or a warm-up activity and a driving question for each investigation, as well as a variety of other kinds of assessments, which we'll unpack a little bit for you later. Now, all the words you see in teal on this slide are assessments of some sort, so you have to create that free account to get access to the assessments. We actually vet you as a teacher to make sure you're real and you're not just a student. So there's usually a little delay between the time you ask to create the account and the time that we open it for you. The rest of that is freely available on the web page, and you can see it without any account. And at this point, I'm going to turn it over to Justine.
Thanks, Artis. Yeah, so here I just have a quick screenshot of what the pretest looks like. So as Artis mentioned, they're short, they're multiple choice questions. You can just use it to see where students' current understanding is at about supernova. And then we tell you all the answers, and it also shows you how each question uses each of the elements from the Next Generation Science Standards. And then the phenomenon activity for exploding stars, we're going to start to dive into this. This is where the modeling piece can start even before students get into the investigation. We want to start by eliciting those student ideas. So what is their current understanding? What do they currently think about some sort of big picture? For exploding stars, we want to think about measuring distances in space and how can we use these supernova to measure distances in space. And this is where we can start to connect things to the AMTA units. So we have there are three different AMTA units, which Dan will talk a little bit more about, Unit 1, 3, and 4 of the astronomy units, and they are all somehow connected to measuring distances in space or type 1A supernova and their light curves as well. So we can start to have students developing these models. They can work together. They can start to do some whiteboarding activities. And here I'm going to turn it over to Dan to start talking about these units and some ideas that you have for the modeling process to begin.
Thank you, Justine. So the AMTA course, Astronomy Modeling with Exoplanets, has 4 units. And the first one is about creating a map around space, understanding how we measure things in space. And this includes creating our models for the celestial sphere, the coordinate systems, and starting to figure out cosmic distances. And we start by learning one of the first rungs of the distance ladder, which is parallax. And the graphic on the right, which you can see a little tiny star shaking back and forth. That's actually not a star, it's an asteroid within our solar system. And if you've ever done the parallax activity with your students, and you hold your finger up and close one eye and then close the other eye, you can see your finger moving back and forth. And we can use some basic geometry from that in order to figure out the distance of an object in our solar system. So we first introduced this idea of how we measure things in space with parallax, using some real data that we give students, and sometimes in some cases we can even collect our own, which is very exciting. And then when we go into our Unit 2, which is about motion and forces and gravity and Kepler's laws, and then in Unit 3, we go more into light. And when we get more into light, we start looking at, how do we create light curves? And we really do focus a lot on exoplanets, but we also look at Cepheid variables and obviously supernovae. But we learned how we can actually do something called photometry. We can actually measure the brightness of light and see how it changes over time. And as we can see in some of the videos we saw earlier, when a supernova happens, we get a pretty bright event that occurs. And in the lower right, should actually have a graphic of a recent supernova called 2023 IXF, which happened just 2 years ago. And if you notice in the graphic, there's it's like a light, someone's turning the light on and off. This is showing us before the supernova and after the supernova. And these objects are so bright that the amount of light that comes out of them can outshine all the light in the galaxy, which is pretty amazing. Super energetic events. So when we measure these, we can do something called photometry. So we actually teach our students in the modeling course on how to do photometry and how to create a model from that. And then in Unit 4, we actually try to understand that model. And I'll talk a little bit more about that later, about what that kind of modeling works. But that's kind of a brief overview of some of the stuff that we do. And I do have a graphic on there too that just kind of give you an idea, this idea of apparent and absolute magnitude. So thinking about these type 1A supernova as standard candles is really important to make sure that we understand that as well.
Thanks, Dan. Okay, so maybe you haven't even introduced supernova to your students yet. We provide you an activity in our phenomenon just to have students look at these past historic supernova and that have happened over time. And if they can start to identify some patterns, we don't tell them what type of supernova it was. We just let them know what the record was of this supernova that happened. So we give them 6 different supernova that they look at. They start to identify patterns, and that's when they can create their initial models of how supernovae can be used to measure distances in space. Then they can get into the investigation, and they'll be able to go back and revisit those models that they started to create as they go through the investigation. There are 4 different sections to the exploding stars investigation, and in between each section, there are checkpoints. And these are great places to stop the instruction, go back, add to your models, revise your models of how you think distance can be used, or how you think supernova can be used to measure distances in space. And you can see how the students' thinking has changed as they progress through each section of the investigation. We'll do some modeling with that later on in our webinar. But the first part of our investigation is just an introduction to different types of supernovae. And so here, they're starting to identify patterns from real data. And then they are introduced to type 1a supernova and type 2p supernova. And they begin to develop these like initial simple models of what their light curves look like. Then they can start to classify supernovae. They'll use models to measure distances to supernovae, and we'll pause and we'll talk more about how they're using models in this section with a widget, with a tool. And then they'll measure distances to supernovae and compare results. So they're going to be using real data this whole time. I talked a little bit about the modeling. This is when we get into section 3 of exploding stars. They're going to be using model light curves to generate real astronomical data. So they're going to be fitting light curves using this widget. We'll explore this together to help everyone make sense of it. And they're going to be generating data from models of type 1a supernova to help us measure distances in space. So what I'm going to do right now is open up the investigation, and I'm going to have you all do this with me. If you go to the links document and click on this top link here in white, Exploding Stars Investigation link, you are going to be directed to this page where you can start the investigation logged in. You might need to create an account, and you can feel free to do that right now. The difference between doing it logged out and logged in is that logged out, it doesn't save your work as you go through the investigation. Same with if you do it, if you log in as a student or create an account as a student. Let me go there for you, create an account. If you join as a student, students will be able to progress through the investigation, but they have to put in all of their answers page by page. It does save their work as they go. But if you do create an account as an educator, you can jump to, let's say, page 20 of the investigation and help students out and jump back to page 10, and you don't have to answer questions each time as you go. So that's one of the advantages of creating an educator account. So go ahead and start the investigation logged in as an educator. And as you guys are creating your accounts, I'm going to point out a few features. On the left-hand side, we have a menu. You can choose the language selection. We have it available in English and Spanish. If you happen to speak a different language, Google Translate works pretty well, and you can just right-click on your screen and you can Google Translate to your preferred language. We can't guarantee that everything is translated perfectly, but we have heard it works out pretty well. We have a table of contents on the right-hand side, which also helps you if you are in an educator account to go to different pages of the investigation, or it just shows you your progress. We do also have a progress bar at the top of our screen here. So as you navigate between the pages, you can see how much of the investigation you have completed. These pins are where our checkpoints are. So they mark the differences between the sections. So if I go to page 8 of Exploding Stars, this is where we are ending one section of the investigation, and you can see the checkpoint is on page 7. So it's just a good place to stop the instruction, do some formative assessment with your students before they start the next section of the investigation, where they're going to be introduced to some new concepts, or they're going to be applying their understanding in a new way. Let's see. Also, something to note is you can expand these graphics. If you click on this expansion image or little icon, you can expand things to get a bigger view if that helps you. Artists, is there any other features I should be pointing out for exploding stars?
I don't believe so.
Okay. I think that's it. So that's just a quick 101 with how to use exploding stars. We're going to put you all into breakout rooms. There should be about 5 people in each breakout room. We ask that one person shares their screen. That just helps to keep everyone together as you go through the investigation. You don't have to read all of the narratives aloud. You can just kind of scan through that and then work on the questions together as a group. And you don't have to type in complete sentences if it happens to be an open response sort of question. The person that is sharing their screen is not in charge of everyone's answers. So I just want to make that clear. You're just kind of helping to facilitate your group, keeping everyone together. And then come back to the main session if you need help with anything. We're going to stop at the end of page 12. So I showed you where those checkpoints were. We are going to do section 1. We're going to skip that first checkpoint, go to section 2, and then stop at the end of page 12. And that's when we're going to bring everyone back to the main session. We're going to give you about 20 minutes to get through those first 12 pages. And then we're going to pull everyone back to this main session together. And we're going to model some formative assessment. Any questions before you go into the breakout rooms? Is anyone having trouble opening up exploding stars on their screen, or any issues with creating accounts? Okay, we can go into breakout rooms, artists. Go ahead and open them.
Well, welcome back, everybody. The page numbers, Kathy, are on the top right where it says table of contents for the investigation. And you can also click open that table of contents and see what page you're on. And your progress bar up at the top.
And at the bottom where it says previous page.
Yes, that's true too. Whatever you happen to see on your screen. Okay, I know not everybody got to this page, and it's a super important page. And this really plays well into the modeling aspect of how we can use type 1a supernovae to measure distance. So it turns out that there is a relationship called the delta M15 relationship that says if you measure the supernova time from, or if you measure the apparent magnitude of the supernova from the time of its peak to 15 days after the peak, that's where the gray shaded box is, the rate of decline changes with the intrinsic brightness of the supernova. So a supernova that fades more slowly is more intrinsically bright. The supernova B here that fades more quickly is intrinsically dimmer, regardless of what its apparent magnitude is. Now here's the interesting part. If you measure the change in apparent magnitude from the top to 15 days after the peak, that's called the delta M15. And that's the number we use to plug into the equation to calculate other things we want to know about the supernova, like how bright it really is, and then how far away it is. So if you didn't get to that page, I thought it was important that we look at that page before we move on. And Justine's going to be doing some formative assessment questions with you now, assuming that you got to this page, page 12.
Yeah, I think the formative assessment questions will hopefully be a little a little easier to grasp than that to start us off. Okay, so they're not trick questions. They're just to make sure that we understand everything that we learned in section 1 and most of section 2. Do not put the answer in chat yet. So we have a document that contains options for just quick formative assessment questions that you can do between each section of the investigation. Sometimes we have like 2 options for you, sometimes we have 3, and we try to provide some different styles, like sometimes they're multiple choice, sometimes they're a short answer. And right now we're going to do a multiple choice question. And this question, I believe it would be great after section 1 for you to do this with your students, just to make sure that they're understanding the patterns that they're seeing in our different supernovae. So what I'm going to have you do is read this question. And you're going to put your answer in chat, but don't press enter or return. Don't submit your answer yet, okay? So I'll give you about 15 seconds or so once I'm done talking to read the question, look at the graph, decide which option is best, A, B, C, or D, put that letter in chat, and then wait for me to say waterfall. And then we'll do a waterfall style of responses. So you'll see a waterfall of answers coming into chat all together. Okay, so I'm going to stop talking. I'm going to give you 15 seconds to read our question here. And then you're going to choose the best answer, put it in chat. Don't press enter. We're going to do waterfall in 5, 4, 3, 2, 1. Press enter. Oh, beautiful. Okay, let's see. You are correct. The answer is C. It is type 1A. It dims steadily after its peak brightness. I think in our formative assessment document, we suggest that students explain how they know it is a type 1A supernova by explaining it to their partner. So I think we set this up as a like think, share, pair sort of question. But for our Zoom platform, waterfall works okay. Okay, and here's your next question. We'll do it the same way as a waterfall style. So you're going to read the question, put either A, B, C, or D in chat. And then when I say waterfall, that's when we will release our answer. So I'm going to give you about 15 seconds to read it and choose the best response. And we're going to do waterfall in 5, 4, 3, 2, 1. Waterfall. Perfect. Very good. So they all have similar intrinsic peak brightness due to the fact that they were about the same mass when they exploded. We have a link here to our ABCD cards. So if you were to present this on the screen, you're teaching in person, you could have these cards in front of you where students can hold up either A, B, C, or D. They can keep their response right in front of them so that their neighbor doesn't see their answer, and their answer is just between you and them. So they hold the card up so no one else can see. And then you're able to decide, can we move on to the next section? Do we need to revisit a few of these concepts together? Do I need to put them back into pairs? Why do you think it's B? Why do you think the answer is D? So start to engage in argument with the person sitting next to you about what the best answer is. Provide evidence, go back into the investigation and do that. But we are in a modeling workshop. So how can we turn these short these short multiple choice questions into some modeling opportunities? And this is just one idea that you could do. So students have done section 1, maybe they've done section 2 as well. And you could have them start to draw models to illustrate why type 1A supernova can be used to estimate distances in space, and why type 2P cannot be used for estimating distances. So they might start to draw a model light curve. They might start to have graphs and some sample data points that you would see. They might go back to their initial models and start to revise those as well. Also, at each of these checkpoints, we have separate questions. If you did the phenomenon activity with the flashcards of these historic phenomena, of these historic supernova that have happened over time, students revisit those supernovae and we reveal additional details or facts about them, or we have them start to think, do you think this was a type 1a supernova or a type 2p supernova? So as I just mentioned, we have a document for these. These are in our assessments online. So you can access all the assessments if you have an educator account set up for that. And now I'm going to turn it over to Artis to just go over a few other science concepts from section 1 and 2 that will help you with the next 2 sections of the investigation.
Thanks, Justine. We want to go over 3 things that we feel are really key pieces to navigate this investigation well. And they're also commonly asked questions. So one is the idea of standard candles. Okay, so like if all these type 1a supernova are supposed to have the same brightness, then why do we need to modify or change them a little bit? And it turns out they aren't all exactly the same brightness. The best I could give you is you can think of a supernova as maybe a 100-watt light bulb, but some of them are really 96 or 98 or 101. And there's a way that we can actually tweak that to figure out what the actual intrinsic magnitude is for each supernova and apply those in a way to be a standard candle. So we like to call them standardized. They can be standardized to determine their exact intrinsic brightness. And the reason they're a little bit different is even though all of them explode at about the same limit of 1.44 solar masses, they don't explode all the same way. There are differences in the ways they explode. There are differences in the densities of their local environments, the age of the white dwarf at the time of the explosion, and specifically, really important, the amount of nickel-56 it has at the time it explodes. Okay, so we can move on. The reason that this is so important for us is by using these type 1a supernovae, we can then get a more accurate determination of the expansion rate of the universe. So we can use these type 1 supernovae to measure the distance to galaxies, and then using a Hubble plot where we plot the distance versus the recessional velocity of the galaxies, we can look at what the Hubble constant is in different times in the history of the universe. And as you can see by the plot on the right-hand side, it changes, right? It changes from what it is now to what it was early in the history of the universe. And by the way, these 2 plots were lifted out of our expanding universe investigation. So if you do this exploding stars investigation, it's a great investigation to precede doing expanding universe. And I think I already went over this specifically, but now that we can measure this delta M15 relationship, which was discovered by research, and there's more information about this in the teacher guide, we can then build a model that helps us figure out the distance to these supernovae.
Yeah, so in these next sections, students are going to get supernova data, and they're going to be using this model, this solid line here. They're going to be able to fit it. So they'll be able to change the width, change the vertical distance as well of this model to fill in the gaps here. So they're using models of supernova to generate data. And before we go into sections 3 and 4, we'll finish our investigation. I wanted to open up to any other ideas or comments, questions that you may have. I wanted to specifically call out, forgive me, I might pronounce your name wrong, but I think it's Mr. Ager. You were in group 1 and you were sharing, you had some fabulous perspective that you were sharing about in your classroom, how you have used the AMTA models, specifically unit 4, when you're talking about distances. I'm just going to go back to the universe's expansion. I believe that you were using this in your classroom, and how exploding stars could fit in that unit perfectly.
this a little bit. So you're just asking like where I use this unit or use this module?
Yeah, or if you had any other insights that you wanted to share. I know you were sharing a lot with group 1 in your group, but if you had any other modeling ideas or things that you do in your classroom with
I
modeling.
don't know if you were there before. I said I'm not a modeler.
Ah,
Don't claim
okay.
to be. I've been to some workshops and things, but I just can't fully embrace the full modeling experience, which I know many modelers do. And so I don't ever want to claim to be a modeler until I can get there fully. But second to that, I do use the astronomy modeling curriculum that's on. I don't remember how I got it. I think I signed up for as a member of the Modeling Association back during COVID and got the curriculum, and it's amazing. If you're teaching astronomy, the 4 units are really, really, really good. I don't do it exactly, again, this is why I'm not a modeler, exactly the way it's laid out. But it's pretty close, with the whole unit 1 being patterns, any patterns in the sky and how we measure space and setting up that first model, and then unit 2 being basically astrophysics and interactions in space. Unit 3 being light and the information we get from stars. I treat that as kind of my stars unit. But I don't do supernova during those 3 things. It's all parallax for distance and the distance ladder during that part. It's not until the changing universe, which is the unit 4, that we introduce the idea that stars can change and the universe changes. And so then that's when this is the first thing I do in that unit, is the supernovas, because kids love supernovas, blow them up and show them this, and then introduce that last piece of the distance ladder to them for this, and then lead them into galaxies and things like that, and then they go off and do their own research on all the cool black holes and neutron stars and stuff like that. Is that what you're talking about?
No, thank you for sharing your perspective and how you used like just even elements from the AMTA units in your classroom or parts of the Rubin investigations as well. Yeah, modeling, you don't have to be an expert in it to just use pieces in your classroom either. Yeah, if anybody else wants to share, now's a good time to do that. Okay.
Justine, before we go into breakout rooms, could you please put back that slide of the model? I think it's, yeah, there, that next one.
Yeah.
I wanted to point out to everybody just a little trick that might be helpful to you. When you use that plot that is on the right-hand side, that interactive widget, the curve width and the vertical offset are a little bit jumpy. You can use the arrow keys on your keyboard to control the speed at which you change them a little bit. And then we notice that some people don't see the directions about using that handle, but that line with the circle on the end of it needs to be adjusted to the top of the curve that you fit, not the top of the data, but the top of the curve. And then that will read out the correct number for you on the y-axis for apparent magnitude. So you just want to mention those 2 things that might be helpful to you as you go ahead and try to fit some of your data. And when you get into the next section, another thing we need to tell you is that the data are randomized. So if there's a group of students in the class, people next to each other won't have necessarily the same light curves.
Yeah, really, really great point. So as you're working together as a group right now, you may all want to focus on one screen and do that together too. You can also do your own as well, but you may all have different supernova that you're working with. Okay, I'm going to have you guys go back into breakout rooms and you can continue where you left off. So say that you didn't finish section 2, you can go back to say page 10, maybe that's where your group left off, start there, and then work through the rest of the investigation. If you have any questions, again, come back to this main breakout room or this main session and we can come help you.
Okay, I'm going to open the rooms now and you'll be in the same room as you were before.
Okay, welcome back. I believe most groups made it to the end of the investigation. Either they almost finished or were about to finish, but you got to the all sky visualization and the histogram for your 3 supernova and where they're located. But I want to open it up to you at this point. Do you have any questions, comments, any ideas that you want to share, anything that you want to bring up? now is a great time to do it. Concerns or strategies? You guys aren't this shy. I was hearing some good discussion as I was popping through.
So this was exploding stars. What were the other modules that you have again?
Good question. So Artist is going to talk about 2 other modules that we recommend following up with, but let me just quickly share those other investigations real quick. I'll go back to that beginning slide. So these are all of our Rubin investigations that are currently available: Coloring the Universe, Stellar Safari, Surveying the Solar System, Observable Universe, Hazardous Asteroids, Exploding Stars, and Expanding Universe. And Artist, did you want to talk a little bit right now, since the question got brought up, about the sequencing for what you recommend with exploding stars and which one to do maybe before or after?
Sure, I can do that. I just wanted to mention that probably most of these are obvious by their titles, what topics they address, with the exception of Stellar Safari. That talks about properties of stars, HR diagram, and finding the distances and ages of star clusters. Coloring the Universe covers a lot of different things: electromagnetic spectrum, filters, wavelengths, building color images that tell a science story. So there's a lot there. Thank you, Heather. We'll check into that. And the 3 investigations that are a really good sequence is to begin with the one that you're working on, Exploding Stars, that talks about how to get the distance to a supernova and therefore its host galaxy. Then use that information in Expanding Universe, because that's how we get the distances to galaxies in that investigation. So that deals with the Hubble plot. And then take that one step further and go back and use those redshift in galaxy information for Observable Universe to look at large scale structure and how the universe, structure of the universe evolves over time.
I hope that answered your question. Are there any other questions or concerns, ideas?
I think in our
Modeling
group we
strategies.
just noticed that it was very specific, and we were wondering how frustrated kids would get with like the 3rd kind of section. So
Yeah, want to elaborate that on a little bit more with what you anticipate for student frustrations when they're in section 3. And just as a reminder, section 3 is when students have random data of supernova, and they're using that model-like curve to generate like its peak magnitudes and calculate its distance.
well, we just kept getting feedback at the end of like, it seems a little high or seems a little low, and it seemed like a little bit of a narrow range for what it would accept. And you could be off by like 0.1, and it would say that it was a little off. Or you could be off by 0.1 in your absolute peak magnitude, and that would give you a distance that was off by like 20, and then it would complain. So I was thinking about my students, like trying to hone in on that, getting very frustrated, having to like go back a page to go back forward. So
I think, Kathy, you have a similar comment about that. And I'll just say that we'll look into that range thing. We tried to calculate it based on the ranges of error that you would make in all 3 measurements. But they have to actually, that practice one has to be input by hand to set the ranges, since there is only one practice one. And the design of this investigation is similar to like if you were doing actual research. Like when you do actual research and come up with answers, you don't know if you're right or wrong, but you're kind of leaning on what you've learned, the techniques and the skills. And we hope that teachers would not grade these investigations as if an answer was right or wrong anyway. But the whole idea is to share kind of the science process, give you a little bit of guided practice and feedback in the beginning, and then turn you loose because everyone will have different data anyway. So I know, Kathy, you made this comment about lesson versus exam, and I guess we don't have very specific definitions tied to these, like Infiniscope must. I'm not sure, because I'm not really familiar with their lesson concept. But you're right, we do not have feedback at every point. We have feedback at the beginning, and then we kind of let go of their hand and let them take it from there.
I'd like to add real quickly to what Artis has saying with as far as modeling instruction is concerned is in a lot of our modeling courses we do try to emphasize with students that it is the process that we want to to value and to really to really encourage the learning process in the classroom. So I appreciate, Artis, you bringing that up. And so I think that would be a great, like, yeah, I would agree with maybe the range, maybe that's something that could be adjusted. But if that does happen with your students, I think that'd be a great time to have a conversation as a class. Like, what does that answer mean? And, is it the answer that's most important? And they're going to say yes, because I mean, that's how we're trained in our education system, unfortunately. I have to continually, remind my students that, yeah, it's important to like come up with an answer to something, but it's not the answer that's important. It's how we got to that answer, and that's the most important thing about, our learning is the process and the discovery and the investigation. So, I think that's, even though it could be frustrating to get there, and to get those wrong answers, not sure why. I think that's a great opportunity to have a discussion as a class and maybe talk about that and see what comes out of that.
Yeah.
Conversation.
I think if like in a normal class for me, I'm doing everything on like whiteboards and paper. And I think there's just something about like typing it into a box on a web page and then having it spit back. It's not quite right, like 3 times in a row, just like hits different somehow than like having it be a conversation with your teacher. So that's where I get stuck. Not like of course, like I have my students getting stuff wrong all the time and then nudging them in a direction, but like it's hard when it's through this like kind of impersonal online system a little bit. Like I could coach them through it. It's just not a system that I think cues them to be their most adaptable selves. So
yeah, it's a good point, and I think what's something you could do, as this activity and investigation evolves, is use the online applet. Students could work in groups, but then put what they find out together. If you have an in-person classroom on the whiteboards, right? And that's what I would probably do. Is I would probably have this be like an investigation that we could do as a class, and they could work in groups. And maybe have one computer per 3 students or so, and then have them work together on their whiteboards as they're going through it, and maybe pick one or a few of them to whiteboard out, and then students can kind of compare in a whiteboard session on what their process was and what their different answers were based off of the different supernovae that they had. And that'd be kind of an interesting thing. And that might not be the only way to do it, but that's just kind of brainstorming out loud of like, if I was doing this in a modeling course, what I might try to do. So that's just one idea. But if other people have ideas too, please share.
Yeah, this is.
So,
Oh, go ahead, Scott.
uh, sorry, I was going to say, as I think about this, I liked the setup of it, especially because like I teach astronomy, so I know this stuff. So I was able to go through the module. I was able to go through it pretty quickly. But thinking about it from the angle of my students, I do feel like it would take them quite a bit of time because it is like 40 something questions. There's a fair amount of like little boxes and things they have to answer. So I'm just thinking about it from the angle of my students. I almost wish the module was shorter in a way, just because, you know, for my high school class, it's 45-minute block. We don't have a block system like undergrad class or like some high schools do. It's just a traditional I see you for 5 minutes, you go away, I see you 45 minutes the next day. This would take my kids probably 2.5 bells to do this. And I almost wonder if the fact that it is kind of does take a bit of time, if they would sort of like lose the thread overnight into the next day. I think that's kind of the only downside I see to it. But I did like the whole module. I thought it was useful. I liked the light curves and I liked the equation comparing the absolute and the apparent magnitude so they can get that relationship. But yeah, I think maybe it's just a little too long for me to do the full module with my students. I may have to chunk it down.
I wanted to just say one kind of neat, cool thing about it. I love how they really have to look at the graph to see that the numbers are going opposite to what they would intuitively think. And then once they figured that out, and then, you know, especially if you can relate it to the magnitude scale right away, I think there's a whole lesson right in that. And so you're right, it would take even longer. But just those little pieces together, I think, or little pieces in chunks like that might make it very informative.
Awesome. Well, thank you all for sharing your ideas. This was a really meaningful discussion. I appreciate everyone's honesty as well. And this is some meaningful and some actionable feedback that we can take back to our team as well. And we understand that everyone's in a different teaching environment and, you know, maybe section 1 and 2 work for your students and you just don't have time to do the rest with your class. And that could be maybe extended learning for them as well. But we appreciate all these ideas that you're sharing and feel free to continue this conversation now in chat. But Artis and I have a few more features that we wanted to share with you before our webinar is over. One thing I wanted to mention, you can always connect back to your bigger picture, the initial models that students were drawing before they even got into the investigation. You can bring up the idea that Rubin is going to discover about 1 million supernovae annually, and about 10,000 of those will be type 1a supernovae. So are there any limitations that we have? This can be a modeling discussion that you can have with students with how using type 1a supernovae as standard candles, there may be some limitations there, and will Rubin Observatory be able to address any of those limitations with using supernova to measure distances in space? So that's just one meaningful conversation that we thought could be a great way to wrap up the exploding stars investigation, especially if you use the phenomenon activity. And I also wanted to point out again this modeling cycle with AMTA, how it's just an ongoing process. And some of the modeling features that we did use in exploding stars is asking questions. So students are, you know, they're leading the learning. They're the people that are guiding this learning process, asking their initial questions about distances in space and supernova. They observe phenomena, and when we say observing phenomena for exploding stars, they're observing light curve data for type 1a and 2p supernova, and they're using that to analyze and interpret data to measure distances in space. And then they're using a model as well. They're using a model of type 1a supernovae to then generate data about their 3 random supernovae. And I'm going to turn it over to Dan to connect back to light curves and citizen science with AMTA.
Thanks, Justine. So with the astronomy modeling workshops, we provide some real data for you to use. In some cases, we actually try to get teachers and students to actually collect data. In previous workshops that I've helped to host, we've had teachers actually get access to the Las Cumbres Observatory, as well as this network called the Unistellar Citizen Science Network, where they could actually get data on some of the investigations that we have. And one thing that we learn in the modeling workshops is how to actually develop photometry skills using FITS files. So if you're not familiar with what FITS files are, it stands for Flexible Image Transport System, and this is just the official file that has all the metadata for astronomical images. So if you're a photographer and you shoot in RAW, you get all of your data, you get the full image file. It's kind of like that. But it's a special type of file that can only be opened on certain type of programs. And there's browser-based programs that you can use on Chromebooks there's one called JS9 that we use. We do curve fitting. We don't have as nice widgets as Rubin Observatory has. So this is one of the reasons I was really excited about partnering with artist Justine and their team, because they have these really nice widgets for us to kind of see how this curve fitting could work whenever we actually are able to actually implement some of the more advanced kind of coding that we would use in a professional setting to curve fit. But we do talk about curve fitting. We do some stuff in the workshop. We analyze and interpret data for supernovae, and we do these whiteboard sessions like you see here in this picture. So these are my alien students from last year, and this is not for supernova investigation, it's for a comet investigation, but they have light curves that they actually created on their own from measuring the changes in brightness of this comet from the Citizen Science Network that we worked with, and they were able to figure out the orbit of it. Go to the next slide. And this is how we actually do it in the astronomy modeling workshops. We are able to take these FITS files of galaxies that have a supernova in it, and we provide those. And you open this in this program called JS9, and in photometry, you put this annulus, this little circular thing like you can see in the bottom left image. And then from that, you can measure the the intensity of the star and put that into a data table, and then spits out a graph. And you can see it's very similar to what you did in your investigation today with the Rubin Observatory investigation for exploding stars. And this comes straight from the data that you get in the astronomy modeling workshop. And as you can see, you get that nice little type 1 supernova curve from this particular data set. And then I just have one more slide to share with you for today. So an exciting thing I like to always talk about, and this is something I focused on in my PhD, is trying to really enforce this idea and learning by doing, and increasing motivation and engagement both for teacher and students. And Rubin's Legacy Survey of Space and Time is going to be this amazing project. It's going to discover all these supernovae, change our understanding of the universe, and it's going to make more data than we can possibly ever use from humans alone. So there's going to be all this citizen science potential. And follow-up observations are going to be really important whenever we discover these new supernovae. So, if, Rubin Observatory is a survey mission, so having other observatories around the world following up on its discoveries are going to be really important for the science that we do. So there's professional observatories that are online now that are going to be coming online in the near future that are going to try to do those follow-up observations for Rubin, but there's still not enough professional observatories in the world. So there are opportunities now for educators to get involved in citizen science to follow up with observations. There's things like Zooniverse, when I know there's going to be some stuff with Zooniverse, the Rubin Observatory happening, but there's also new types of telescopes, digital telescopes that you can use to collect data. That's what I was involved with Unistellar. And the example here is from the Pinwheel Galaxy, the supernova 2023 IXF, which I think is actually in the Rubin Observatory module. And we actually had citizen scientists using these small telescopes, as you can see in this picture here. That was actually at the Rubin Community Workshop. That's not when we took this data, but that's where that picture came from. And that got published in a paper where we were able to create the light curve for that supernovae. And teachers and students and just your average people using the small telescopes are able to do that. So I just want us to try to imagine like a future where teachers and students can learn by doing, and maybe even publishing in peer-reviewed journals. Maybe not being the writer yourself, but maybe imagining the data that you collect with your students being inserted into these papers. And that has happened, and it currently is happening too. And that whole idea of modeling instruction is something that leads toward that. And I know Rubin Observatory and the education team, this is something that's going to be, I think, pretty exciting in their future as well too.
Thank you, Dan. We anticipate that once our data starts coming in, we'll have more than 100 new citizen science projects on Zooniverse within the first year. So there's going to be a ton of things to explore.
That's awesome.
I'm going to go pretty quickly through the end of this because I want to respect your time, and I realize we're just a few minutes from ending. But I wanted to show you a couple different ways you could assess this investigation. As one of you mentioned, there are a lot of questions in each investigation, so the idea of going through and grading each one right or wrong just isn't very practical. So we've created these charts for each investigation called key assessment questions that are kind of like the questions, if you spot check them and the students know what they're doing on these questions, chances are they've done everything correctly up to that point. Notice there are different rows here that address different kinds of SCPs or core ideas, cross-cutting concepts. So if you only focus on, let's say, using the mathematical relationships, you might only use row 2 there on this particular chart. We have a lot of different assessments. This one is really great for modeling. This is a great whiteboarding activity if you wanted to do it in groups. Now that students have kind of gotten the idea of the types of supernovae and their light curves, we ask them to sketch out supernovae, and then we ask them to alter their model as we go along. You just see the first question here. It comes with a scoring rubric where 3 is kind of like meets the standard and 4 exceeds it. And those scoring rubrics are also aligned to the NGSS standards that are being addressed. We've already mentioned formative assessment, and Justine did some of those with you. I wanted to point out that our formative assessment, our pre-test, post-test, summative, those are all available as downloads that you can modify. Maybe pick and choose what you'd like to take out of them. So they're available as Word documents as well as PDFs. Something new that we just introduced a week ago is that some people have been asking for answer keys, and you can see Justine here on the assessment page of the Exploding Stars, and you can see there's 6 different kinds of assessments you can choose. Number 6 is the new one. It's a partial answer key for investigations. I say partial because, as you know, data are randomized and some questions are open-ended. So we've provided some guidance there, but not a complete exact answer key. And these are available right now for 5 of our 7 investigations. We can skip this because this was the sequence we were talking about a little earlier. I wanted to mention to you that if you would like us to do a workshop on Rubin Observatory investigations, just contact us. If you would like to learn more about any other investigation, we have recordings of all of our webinars for all of the investigations on our professional development page. We also have a community of practice. I know some of you are already in it, but this is kind of like our inner circle of Rubin users, where we post questions and have conversations from time to time and give you news of what's coming and new for our education pages. And so if you'd like to join that, you can either join the Facebook group by just looking for Rubin Observatory educators, answering the questions, agreeing to the rules, or if you prefer not to do social media and you can fill out our evaluation in a minute, just check the box that say you want to be added to that list. We have another webinar on exploding stars coming up on April 23. This is going to be a new series that we're kicking off called Behind the Scenes, and it's going to address some of your deeper questions about how is an authentic data analysis process work? How did we pre-reduce things? A little bit understanding better of the science, tips on how to use things, kind of a more in-depth look. And this is especially good if you want to do a deeper dive into the science, or you just feel like you need a little bit more understanding in order to effectively teach this. So Justine has just put the link to the registration form in chat. If you're interested, please register by April 21, and we'll look forward to seeing you there. And Dan, I don't know if you'd like to say anything about this slide, but this is the AMTA slide.
I'll just add that I highly recommend the Science Modeling podcast. I've found it really insightful to listen to other teachers that use it, both at the middle, high school, and even college and university level. And you get to hear from some of the developers from modeling instruction. There's some older episodes where you can actually hear from the researchers who actually first started modeling instruction in the 90s. So it's a pretty cool podcast if you're looking for something to listen to on your drive, or whenever, to help you kind of think about modeling, and you can learn a lot from it.
My understanding is there's also one with Daniel Peluso.
I don't want your ears to bleed from hearing my voice too much. But yes, there's I think one with me in there too, talking about astronomy modeling. So yeah, thanks for sharing, Emma. And Emma was in one of our modeling workshops. So Emma, it was really good to see you in here. And thanks again for giving some of your feedback.
Yeah, it's been, this was great. I'm glad that I was able to drop into this. And yeah, love doing more astronomy with kids.
Okay, well, this is the end of our presentation. We're happy to stay around for a little while if you have more questions or comments. If you could, please fill out these two surveys. They're both very short. We would appreciate it. The first one is the AMTA webinar survey. The second one is our workshop evaluation. And especially if there's something you didn't have a chance to say, but you'd like to say it to us so that we can make these even better for you. There's space on the evaluation for Rubin Observatory where you can add that information. Again, I want to thank you for coming tonight. I know how busy you are. We've all been there, done that, so really appreciate your time. We appreciate your input. And if there's any way that Justine and I can help you, please contact us. You have our email addresses here, and we'll be sending out a copy of these slides and a link to the recording once it's available.
Thank you so much, Artis and Justine, for hosting these Rubin Observatory workshops. They're awesome.
Yeah, thanks everyone. And thanks again for the meaningful conversations. It's like Artis said, we listen and we take your feedback and we try to make these investigations even better for you.